Okay, we are finally ready to prove that the fundamental solutions to a matrix equation Ax equals 0 are actually a basis of the null space for A. So let's look at how to do this. It's just a matter of piecing together a lot of results that we've already proved. So I've written most of this up, but we're going to go through it quite slowly and just remember all of the things which we've proved which we need to help us. So the theorem, which we're going to prove, says that the fundamental solutions to the matrix equation Ax equals 0 are a basis of the null space N of A. So you'll remember the null space just means the set of solutions to that matrix equation. And the proof goes via row-reduced echelon form. So we take R to be a row-reduced echelon form matrix that you can get by doing row operations to A. And we'll introduce some notation, so we'll say that A and R are M by N matrices, M rows and N columns. So we're also going to give names to the number of columns with leading entries and the number of columns with no leading entry in R. So we'll suppose that R has R columns, lowercase r columns with leading entries and K columns with no leading entry. So of course every one of the N columns either has a leading entry or it doesn't, and therefore R plus K is equal to N. So if we go down to the example in the bottom right here, you have 1, 2, 3 columns with no leading entry, and the other 2 columns do have a leading entry. So let's figure this out, what's going on. This is our example R. We have M, the number of rows is 3. We have N, the number of columns is 5. And we have 2 columns with leading entries, so R is equal to 2, and K columns with no leading entries, K is equal to 3. And 2 plus 3 is equal to 5, as promised. Okay, so we're happy so far. So we now introduce the linear map TR, which goes from F to the N to F to the M, where F is whatever field the entries of the matrices A and R belong to, so perhaps the real numbers or the complex numbers or whatever. We introduce the linear map TR, which is left multiplication by R. And the reason to do this is because once we've got a linear map, we can start using the rank nullity formula, and we actually know what the image and the kernel of TR look like in terms of other characters that we've already met. So we saw in our examples on images, we saw that the image of TR is the column space of R, the set of all linear combinations of the columns of R. And we also saw that the kernel of TR was equal to the null space N of R. So that's pretty much by definition. But there's one other important equality, which is that we showed some time ago that when you do row operations to a matrix, like A, you don't change what the solutions to Ax equals 0 are. So the solutions to Ax equals 0 are the same as the solutions to Rx equals 0. So this equality here, which one? This one, is because row operations don't change the set of solutions to a linear equation. Doing row operations to the augmented matrix don't change the solutions. So that is theorem 3.9.1. Alright, so we want to use the rank nullity theorem, and the rank nullity theorem says, the rank nullity theorem applied to TR, this linear transformation TR, says that the dimension of the image of TR plus the dimension of the kernel of TR is equal to the dimension of the domain of TR. So the dimension of the domain is n, because that's F to the n, the space of height n column vectors. The image of TR is the column space, and the kernel of TR is the null space of R, which is equal to the null space of A. So what the rank nullity theorem tells us, putting those things together, is the dimension of the column space of R plus the dimension of the null space of A is equal to n. So now we're going to use some more results that we proved. So one of the things we showed was that we identified these fundamental solutions and proved that they were linearly independent. So the K fundamental solutions to Ax equals 0. So there are K of them because there was a fundamental solution for each column with no leading entry. So the K fundamental solutions are linearly independent. Okay, we proved this a few videos ago. I think that was lemma 4.11.2. Okay, so you have k linearly independent elements inside the vector space n of a. So if there are k linearly independent elements, then the dimension of n of a is at least k. Okay, that we actually wrote this down. That was a corollary. It was corollary 4.13.1. So those k fundamental solutions, we know they're linearly independent, so the dimension of the vector space they belong to, the dimension of the null space of A, is at least k. All right, what can we say about the column space of R? Well, what we can say is the R columns of R. It's not a very good way to spell columns. Let's try again. Columns of R which contain a leading entry well, remember, R is in row reduced echelon form, so those columns are actually standard basis vectors. They have a 1 in one position and zeros everywhere else. So to go back to our example on the bottom right of the screen there, it's columns 2 and 3 which contain leading entries, and you can see that columns 2 and 3 are distinct standard basis vectors. The column 2 is 1, 0, 0, and column 3 is 0, 1, 0. Now the standard basis vectors are linearly independent because they form a basis. So they're linearly independent. So what can we say? We get that the dimension of C of R, it contains these R linearly independent things, so the dimension, again by corollary 4.13.1, is at least R. Okay, what have we got now? So let's get rid of some of this highlighting, and I want to go back and look at this thing. I want to look at this expression here. So what we've just shown in green down here tells us that this thing is greater than or equal to R. Okay, that wasn't my best arrow, but let's get rid of the arrow. The dimension of C of R is at least R, because we've just seen that it's got R standard basis, R different standard basis vectors in it. And the other thing that we proved just here was that this thing, the dimension of the null space, must be at least R. Must be at least k, sorry. Okay, but R plus k is already equal to n. So that was because every column, every one of the n columns either had a leading entry or it didn't. So R plus k has got to be equal to n. Okay, so dimension of C of R can't be strictly more than R, because if it was, then C of R plus the dimension of C of R plus the dimension of n of A would be bigger than R plus k, so it would be bigger than n, but it isn't, it's equal to n. And similarly, the dimension of n of A can't be bigger than k, because if it was, then the dimension of C of R plus the dimension of n of A would be bigger than R plus k, which is bigger than n, but it's not, it's equal to n. So actually both of those inequalities must be equalities. The dimension of C of R must be R, and the dimension of n of A must be k. So let's go on to a new slide. It must be, since R plus k is equal to n, it must be that the dimension of n of A is equal to k, and the dimension of C of R must be equal to R. Otherwise, if one was strictly larger, then dim C of R plus dim n of A would be greater than k plus r equals n, and that's impossible because by the rank nullity theorem the sum of those two dimensions is equal to n. Okay, it must be that this happens. Right, so we're now done. Now we have that the fundamental solutions are k linearly independent elements of the vector space n of a, which has dimension k. Okay, if you have k linearly independent elements in a vector space of dimension k, then they are a basis. Okay, so we've proved that the fundamental solutions are a basis for n of a, the null space of our matrix A. And we now are in a position to actually calculate bases by following our row-reduced echelon form procedure. So I hope what this illustrates is how much work we've done and how it now pays off, especially the rank nullity theorem. It allows us to prove all kinds of things which would be rather tricky to do without the technology like the rank nullity theorem.